Hello everyone. In this video, we are going to discuss about energies of orbitals from the chapter 2 Structure of Atom, class 11 Chemistry. You see, hydrogen atom, it is a single electron atom. Only one electron is present in hydrogen atom. See, the energy of an electron in a hydrogen atom, it is actually determined by the principal quantum number n. So, if you consider different orbitals 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, etc. in an hydrogen atom, the energy of the orbitals increase as 1s is having the least energy, 2s is having an energy which is greater than that of 1s, and 2s and 2p, they have the same energy. Okay, 2p has less energy than 3s. 3s, 3p and 3d, all the three are having the same energy. And this energy is less than that of 4s, 4p, 4d and 4f, which are actually equal. Okay, that is, in a hydrogen atom, the energy of the orbitals increase with the principal quantum number. So, if you consider 2s, if you consider 1s, its principal quantum number is 1. If you consider 2s, 2s or 2p, the principal quantum number is 2. So, its energy will be greater than that of 1s. If you consider 3s, 3p, 3d, the principal quantum number is 3. So, as principal quantum number n increases, the energy of the electron in the hydrogen atom increases. So, this electron in these orbitals will have more energy than these orbitals. Clear? You see, the energy level diagrams for a few electronic shells of hydrogen atom is depicted here. You see, this is for 1s, then 2s, 2p. Here we have for 2p, we have denoted it by 3 lines. Why? Because 2p has 3 orbitals. No, that's why. S has only 1 orbital, p has 3 orbitals. No. Okay, then if you consider 3s, 3p and 3d, you see they all have the same energy. That is why they are along the same level. Okay, but 3p has 3 lines here. Why? Because p has 3 orbitals, px, py, pz. D has 5 orbitals, that is why 5 lines here. Alright. So you see, 2s and 2p has greater energy than 1s. 3s, 3p and 3d are having greater energy than 2s. But these are having same energies. Okay. The shapes of 2s and 2p, these two orbitals are different. But an electron in the 2s orbital will have the same energy as that of an electron in the 2p orbital. That is, the shapes of 2s and 2p orbitals are different, but an electron in the 2s orbital or in the 2p orbital has the same energy. Similarly, the shapes of 3s, 3p and 3d are different. Okay, but an electron in the 3s orbital or an electron in the 3p orbital or an electron in the 3d orbital, they have the same energy. So, the orbitals having the same energy are called degenerate. The orbitals having the same energy are called degenerate. See, the 1s orbital in a hydrogen atom corresponds to the most probable most stable condition, and it is called the ground state. Okay, and an electron residing in this orbital is more strongly held by the nucleus. An electron in the 2s, 2p or higher orbitals 3s, 3p, 3d, etc. in a hydrogen atom is in the excited state. Okay, so an electron in the 1s orbital is in the ground state. An electron, that is the most stable, the state. An electron in the 2s, 2p or the higher orbitals 3s, 3p, etc. actually it is said to be in the excited state. You see, orbitals for the same value of n have the same energies. Okay, you see, 2s orbital, the principal quantum number n is 2. 2p orbital, the principal quantum number n is 2. Okay, so same principal quantum number, same energy. That is why they are along the same level. Okay, but what about their azimuthal quantum number? This is s orbital, so azimuthal quantum number is 0 for s orbital. This is p orbital, so azimuthal quantum number L is 1 for the p orbital. Okay, so you see the orbitals for the same value of principal quantum number n have the same energies. even for different azimuthal quantum number L for hydrogen atom. Now, if you consider a multi-electron system, that is hydrogen atom has only one electron, so it is a single electron system. So, if you consider multi-electron system, that will have, I'm not a system, it is multi-electron atom. Okay, so if you consider a multi-electron atom, that atom will have more than one electrons. Okay, so the energy of electron in a multi-electron atom, that depends not only on the value of the principal quantum number n, but also on the value of azimuthal quantum number L. Okay, so you see the energy of an electron in a multi-electron atom depends not only on the principal quantum number n, but also on the azimuthal quantum number L. See, for a given value of the principal quantum number n, see, S, P, D, F all have different energies. That is, if you consider the shells 3s, 3p and 3d, if you consider these orbitals 3s, 3p and 3d, their principal quantum number n is the same. But what about their azimuthal quantum number? For S it is 0, for P it is 1 and the azimuthal quantum number L for D it is 2. Okay, so for a given value of n, S, P, D, F, etc. all have different energies. That is, the energy of 3s is not the same as energy of 3p, which is not the same as energy of 3d. Okay, and energy of 4s orbital is less than that of 3d orbital. Energy of 6s orbital is less than that of 5d orbital. Energy of 4f orbital is actually less than that of 6p orbital. See, the main reason for having different energies of the subshell, it is the mutual repulsion among the electrons in a multi-electron atoms. That is, if you consider a multi-electron atom here, this one is a nucleus which is having a positive charge. There are 2 electrons in the n equal to 1 shell. This is the inner shell, and there is an outer shell here which is for n is equal to 2, and there are 3 electrons in the outer shell. So you see, the electrons in the outer shell are attracted to the nucleus, but the inner shell electrons repel them. You see, the positively charged nucleus and the negatively charged outer shell electron, there will be an attraction between them. Okay, this red one actually represents that attraction. But there are inner electrons which are having the same charge as that of the outer electrons, because all the electrons are having the same charge negative now. So there will be a repulsion between the outer electron and the inner electron, this outer electron and the inner electron, and this inner electron and the outer electron. There will be a repulsion between this inner electron and the outer electron. Okay, so you see, due to the presence of electrons in the inner shell, the electrons in the outer shell will not experience the full positive charge of the nucleus. Full positive charge of the nucleus means Z into E. Okay, Z is the atomic number, is the charge of an electron. Okay, the same number of electrons will, same number of protons will be there in the nucleus now. And proton and nucleus are having almost the same charge now, that's why. So you see, the effect will be lowered due to the partial screening of the positive charge on the nucleus by the inner shell electrons. This is known as shielding of the outer shell electrons, okay, by the inner shell electrons. That is, due to the presence of the electrons in the inner shell, the electrons in the outer shell will not experience the full positive charge of the nucleus. That effect is actually lower due to the partial screening of the positive charge on the nucleus by the inner shell electrons. So that is actually known as the shielding effect, or the shielding of the electrons in the outer shell, that is outer shell electrons, from the nucleus by the inner shell electrons. And the net positive charge experienced by the outer shell electrons, that is actually known as effective nuclear charge, Z effective into E. Okay, effective nuclear charge, that is a net positive charge experienced by the outer electrons, that is known as effective nuclear charge. See, both the attractive and repulsive interactions depend upon the shell and the shape of the orbital. Okay, in which the electron is present. Electrons present in the s orbital. Okay, see, electrons present in the spherically shaped s orbital shields the outer electrons from the nucleus more effectively as compared to electrons present in the p orbital. The electrons present in the spherically shaped s orbital shields the outer electrons from the nucleus more effectively as compared to the electrons present in the p orbital. The electrons present in the p orbital will shield the outer electrons from the nucleus more than the electrons present in the d orbitals. Even though all the orbitals are present in the same shell, this happens. So, due to the spherical shape of the s orbital electron spends more time close to the nucleus in comparison to p orbital electron. The p orbital electron spends more time in the vicinity of the nucleus in comparison to d orbital electron. For a given shell, that is for a given value of principal quantum number n, we know that for k shell n is equal to 1, for L shell n is equal to 2. So for a given shell, that is for a given value of n, the effective charge experienced by the electron decreases with the increase of the azimuthal quantum number L. That is, for s orbital, azimuthal quantum number L is equal to 0. Okay, so the effective charge experienced by the electron will be more. That is, s orbital electron will be more tightly bound to the nucleus than p orbital electron. Because the effective force experienced by the electron decreases with the increase of L. So here the L value is least. So the effective force experienced by the electron will be more. Okay, they are inversely proportional, that's all. The effective force experienced by, effective charge experienced by the electron, it is inversely proportional to the azimuthal quantum number. As L decreases, the effective charge experienced by the electron increases. So for the s orbital, L value is 0, which is very less, no? Okay, so the effective force experienced by the electron will be more compared to the p orbital electron. For p orbital, L value is 1. Okay, so azimuthal quantum number has increased. So the effective charge experienced by the electron will be less. Okay, so for p orbital, L is equal to 1. That is, the effective charge experienced by the electron is less than, in the case of p orbital, but it is better tightly bound than the d orbital electron. See, the energy of electrons in the s orbital will be lower or more negative than that of the p orbital electron, and p orbital electron will have less energy than that of the d orbital electron. The energy of s orbital electron will be less than that of the p orbital electron. The energy of the p orbital electron will be less than that of the d orbital electron. Since the extent of shielding from the nucleus is different for electrons in different orbitals, it leads to the splitting of energy levels within the same shell or within the same value of principal quantum number n. You see, the energy of the orbital depends on the values of principal quantum number n and the azimuthal quantum number L. There is a rule, there are actually two rules. The lower the value of n plus L for an orbital, the lower its energy. That is, if n plus L is less, energy will be less. Now, if two orbitals have the same value of n plus L, when you compare two orbitals, the one which is having less value of n plus L will have less energy. But if the two orbitals have the same value of n plus L, then the orbital with lower value of n will have lower energy. Okay, so when you consider two orbitals, the one with less value of n plus L will have less energy. But if both the orbitals are having the same value of n plus L, then the one with less value of n, principal quantum number n, will have less energy. So let us see one table which illustrates this rule. This is actually the n plus L rule. Okay, this is actually the n plus L rule. So you see this table actually shows the arrangement of orbitals with increasing energy on the basis of n plus L rule. So here in the first column we have the orbital, second column we have the value of principal quantum number n, third column we have the value of azimuthal quantum number L, and fourth column value of n plus L. Okay, so you see when you consider 1s orbital, its principal quantum number is 1. For s orbital, azimuthal quantum number is 0. So what about the value of n plus L? 1 plus 0, which is equal to 1. When you consider 2s orbital, principal quantum number is 2. Azimuthal quantum number for s orbital is 0. So n plus L is 2 plus 0, which is equal to 2. When you consider 2p orbital, principal quantum number n is 2. For p orbital, L is equal to 1. So n plus L is 2 plus 1 is equal to 3. So you see, when you compare this 2s and 2p orbitals, okay, when you compare 2s and 2p orbitals, n plus L is 2 for 2s orbital, n plus L is 3 for 2p orbitals. So according to the n plus L rule, the one with lower n plus L value will have lower energy. So 2s orbital will have less energy than that of 2p orbital. Okay, now when you consider the 3s orbital, principal quantum number n is 3. For s orbital, azimuthal quantum number is 0. So n plus L is 3 plus 0, which is equal to 3. Okay, when you consider, so you see when you compare these two, for 2p orbital, n plus L is 3. For 3s orbital, n plus L is 3. Same n plus L. So you see, according to this n plus L rule, if both the orbitals are having the same n plus L value, then the one with the lower value of principal quantum number n will have lower energy. That is, you see, here both the 2p and 3s orbitals are having the same energy. So the 2p orbital, its n value is 2. For 3p it is 3. So the one with the lower value of n will have lower energy. That means 2p orbital will have less energy that of 3s orbital. Okay, 2s orbital has lower energy than 3s orbital. Similarly, when you consider 3p, n value 3, L value 1. So 3 plus 1, it will be equal to 4. For 4s, it will be 4 plus 0, which is 4. So when you compare 3p and 4s, you see both 3p and 4s orbitals are having the same n plus L value. So the one with the lower value of principal quantum number will have lower energy. So you see 3p will have lower energy than 4s orbital. Okay. Now, when you consider this 4p orbital, we will talk about this 3D later. When you consider this after 4s, I am just considering 4p. So principal quantum number n is 4. Azimuthal quantum number for p is 1. So 4 plus 1, which is 5, the n plus L value. Okay, and when you consider 3D orbital, n value 3, for d orbital L value 2. So here 5, n plus L value is 5. So when you compare 3D and 4p, okay, when you compare 3D and 4p, both are having the same n plus L value. So the one with lower n value will have lower energy. So 3D will have lower energy that of 4p. Okay, and when you compare 4s and 3D, see, after 3p I have written it as 4s. Why? Because when you compare 4s and 3D, n plus L value is 4 for 4s, n plus L value is 5 for 3D. So the one with lower n plus L value will have lower energy. So 4s will have lower energy than 3D. So that is why 4s written here, and after that only 3D written here. Okay, so I hope you got an idea about the n plus L rule. So you see, this is a figure which depicts the energy levels of multi-electron atoms based on this table. So 1s, 2s. So you see 1s, which is the ground state marked here. Then 2s orbital is here. Then when you consider 2p orbital, its energy is greater than that of 2s orbital. For a multi-electron system, for a single electron system, they were having the same energy. But for a multi-electron system, 2p is having greater energy than 2s. So 2p, after 2s only we have drawn this 2p. For p orbitals, there are 3 p orbitals. No, px, py, pz. That is why 3 lines here. Then 3s, which is having more energy than 2p. Okay, that is by 3s here. Then next you have you see 3p. 3p has more energy than 3s, so this is actually 3p. Okay, then 4s has more energy than 3p, so 4s. Then you see after that you have 3d, so 3d. Okay, it is in the increasing order of energy. So for s only one line, because s orbital, I mean s has only one orbital. For 3 there are 3 lines here. Why? Because there are 3 orbitals for p subshell. When you consider the d, it has actually 5 d orbitals. No, that is why 5 lines here. Alright. So this figure actually depicts the energy levels of multi-electron atoms based on this table. And you see, the energies of the orbitals in the same subshell decrease with increase in the atomic number. That is, you see, when you consider the atomic number of hydrogen, lithium, sodium and potassium, we know that the atomic number of hydrogen it is less than that of lithium, which is less than that of sodium, and atomic number of sodium is less than that of potassium. So you see the energies of the orbitals in the same subshell decrease with increase in the atomic number. That is, when the atomic number increases, the energy decreases. Or when the atomic number decreases, energy increases. Okay, so when you consider the energy of 2s orbital of hydrogen atom, when you consider the energy of 2s orbital of hydrogen atom, it will be greater than that of the energy of 2s orbital of lithium atom, which will be greater than that of the energy of 2s orbital of sodium atom, and that will be greater than that of the energy of 2s orbital of potassium atom. Why? Because when the atomic number decreases, energy increases. All are for the same subshell. Okay, 2s. Okay, we are considering the 2s subshell for all the 3-4 atoms. So here for hydrogen atom, its atomic number is the least among these 4. So its energy will be the most among these 4. Okay. So in this video, we have discussed about the energies of orbitals. I hope it is clear to you. And you see all other topics are also from this chapter available in the playlist. Please go through that. Thank you.